This is an approximate law, not exact. It is applicable only to metals. It says that atomic weight multiplied by specific heat in calories per gram is nearly 6.4. We are just interested in it from applications perspective. Some problems can give specific heat in place of atomic weight. So in such problems, we will use this law to find out the atomic weight. Let me give you an illustration. Suppose there is some metal chloride MClX. You want to find out what is X. So it is given that 0.22 grams of it react with 0.51 grams of silver nitrate. Specific heat of metal is 0.057 calories per gram. What is the molecular formula of metal chloride? Or in other words, what is X? .22 grams of this metal chloride are reacting completely with 0.51 grams of silver nitrate. One way is that you write the balance equation and use the mole concept. Other way is that you do not write the equation and make use of the equivalence concept. We are going to make use of equivalence concept here. They are reacting with each other completely. So you don't have to worry about the limiting reactant concept. Equivalence of MClX equal to equivalence of AgNO3. So equivalence means grams weight 0.22 over equivalent weight of MClX. Now, specific heat 0.057 calories per gram. Unit is looking perfect. So for M, divide 6.4 by 0.057. 6.4 by 0.057. It comes out to be 112.28 something. That's the mass of capital M. So 112.28 plus chlorine 35.5, X times, chlorine will come X times, whole divided by the X, the valency factor or the X. What is X here? Chloride ion has -1 charge and there are X. So X into 1 is X. Right? So equivalent weight will have the same X here. That is there in MClX, same X. Now that is equal to equivalence of silver nitrate. So gram weight 0.51 over equivalent weight of silver nitrate. So mass of silver nitrate, silver is 108, nitrogen 14, oxygen 16 into 3, 48. Whole divided by charge on cation, you can take silver plus 1. So the X vector or valency, that is 1 for silver nitrate. Now you have got some math to do. Find out X from this and see if it comes out to be 3 or not. If you have any questions, then let me know. I suppose we can proceed now and take another case. Here is another case in which specific heat of metal is given. A hydrated chloride of metal contains 18.26% metal and 32.42% chloride ion by weight. The specific heat of metal is given. What is this hydrated chloride? Specific heat unit is looking okay, calorie per gram, for this formula to work. So 6.4 divided by 0.16. And that comes out to be 40. From 40, we can identify this metal, which metal has got this much atomic mass, calcium. So the chloride should be CaCl2, but it is hydrated. So there should be some molecules of water present in it. So it should be CaCl2 dot XH2O or YH2O. And that Y or X we do not know. That is why we are given more information. 18.26% calcium and 32.42% chlorine. Besides calcium and chlorine, it has got hydrogen and oxygen. Let's consider 100 grams, then 18.26 grams calcium is present and 32.42 grams chlorine is present. So how many grams water is present? 100 minus 18.26 minus 32.42. So in 100 grams of water comes out to be 49.32. 100 minus 18.26 minus 32.42. That is 49.32. So 49.32 percentage water is there. Percentage. Let me write it here. Numerator is coming out to be 49.32. Now look at this. You are interested in Y. What is Y? Ratio of moles of water to moles of calcium. That is Y. Calcium has got 1 here, water has got Y here. So what is Y? Moles of water divided by moles of calcium. We know that mass of water is 49.32 grams if we take 100 grams of the sample. So moles of water will be 49.32 over 1/8. Then moles of calcium would be, calcium is 18.26% divided by 40. That should be Y. Just calculate this. See how much are you getting for Y. Yes, carry on.
Sir, over here you have taken moles of H2O upon moles of Ca is equal to Y. Sir, is that being deduced from here itself, or is that some universal kind of approach?
It is deduced only by looking at this formula. Only by looking at it.
So this comes out to be 6.002 or 6.
6.002. That means 6. Any questions? Let me know. All right. So in miscellaneous discussion, that is one thing I wanted to cover. Another thing is molarity of water. You know the definition of molarity. It is moles of solute per liter of solution. If we have just water, then clearly the concept of molarity, which is about moles of solute per liter of solution, it is more of academic interest. We think like this, that suppose we have got 1 kg of water, 1 liter of water. 1 liter of water is same as 1 kg of water. Then how many moles of water are present in that 1 kg? How many moles? And that's very easy to find out. Moles of water will be gram weight, which is 1000 grams in 1 kg. Gram weight divided by 18 for water. So moles are going to be 1000 by 18, right? And molarity is mole per liter. Moles are 1000 by 18 and liter is 1. Whole divided by 1. So the answer will be just 1000 by 18 and it comes out to be 55.6 nearly if you divide 1000 by 18. .56 to be little more accurate. 55.56. But most of the times we talk about some solute dissolved, and in that context we talk about molarity. Yes, any questions? Let me know. Now, I have to discuss one more important thing. Strength of hydrogen peroxide solution. Hydrogen peroxide has a special way telling about its strength. That is what you have to understand now. Hydrogen peroxide has some special way of telling its strength. Otherwise, generally for solutions we talk about molarity. The most common practice is molarity. Then what is this way for hydrogen peroxide? It is like this. Certain volume. For example, we can say it is 20 volume hydrogen peroxide. What is the meaning of 20 volume hydrogen peroxide? 20 volume hydrogen peroxide means that if you take 20 milliliters of hydrogen peroxide, then it will give 20 milliliters. Rather, if you take 1 milliliters of hydrogen peroxide, then it will give 20 milliliters of oxygen at NTP. 20 volume hydrogen peroxide means if you take 1 milliliter of hydrogen peroxide, it will give 20 milliliters of oxygen at NTP. Which reaction gives oxygen in hydrogen peroxide's case? 2H2O2 giving twice H2O plus O2. It's a very simple reaction. 2H2O2 giving twice H2O plus O2. It's like decomposition basically. So twice H2O2, 1 times O2. It is a 2:1 ratio basically between hydrogen peroxide and oxygen. Remember, when we say 20 volume hydrogen peroxide, we are saying 1 ml of hydrogen peroxide will give 20 ml of oxygen at NTP. It is the NTP of oxygen. Oxygen is the gas. We are not saying hydrogen peroxide is at NTP. Hydrogen peroxide is some liquid. So 1 ml of that liquid when you take, hydrogen peroxide liquid, solution when you take, and you have this reaction, then you find that oxygen that is liberated, that is so much in volume at NTP. If the solution of hydrogen peroxide that you took was stronger, it would give more oxygen. Stronger solution, more oxygen it will give. Dilute solution, less oxygen it will give. So when I say 20 volume hydrogen peroxide, 1 ml is giving 20 ml oxygen. If I have got 40 volume hydrogen peroxide solution, then it means 1 ml of hydrogen peroxide is giving 40 ml of oxygen. It is more concentrated. I hope the definition is clear. Any questions about the definition part, let me know. Then let me go to the illustration part. A solution of potassium permanganate containing 3 grams per liter is used to titrate a solution of hydrogen peroxide containing 2 grams per liter. Hydrogen peroxide is liquid. What volume of permanganate solution will be required to react with 20 ml of the hydrogen peroxide solution? What is the strength of the hydrogen peroxide solution in terms of available oxygen? This is what I was saying, in terms of available oxygen. So when we say 20 volume hydrogen peroxide, 20 volume, it means we are telling it in terms of available oxygen. Right? Alright, so the last part is just asking us that whatever answer we have got about concentration, that we must tell in terms of the available oxygen. So before this part, it is the usual approach that we say in titration. The usual approach in titration is that you just say that the equivalents are same. So if you are titrating acid with base, or if you are titrating potassium permanganate with hydrogen peroxide, you just have to say that the equivalents are same after looking into the limiting reactant point. But here there should be no problem of limiting reactant in titration. In titration you add the volume very carefully so that you just have the bare minimum required. So that problem should not come here of limiting reactant. So you just say the two equivalents are same, KMnO4 and hydrogen peroxide. Equivalents means N1V1 equal to N2V2. N1V1 equal to N2V2. Now, potassium permanganate solution was 3 gram per liter solution. 3 gram per liter is not telling molarity, it's not telling normality also. We will have to find normality. That's very easy. Gram per liter, but we want mole per liter or equivalents per liter. Let's say we want moles per liter. Then KMnO4 means, can you calculate the mass of KMnO4 and see if you are getting 158. Potassium you can take 39, manganese you can take 55. So potassium 39, manganese 55, oxygen 4 means 64, 158. Molarity of KMnO4 solution is 3 divided by 158. But I don't want to write balanced equation. I just want to use equivalence concept, N1V1 equal to N2V2. So I need normality. And the problem is that this is a redox reaction. Reaction of KMnO4 with hydrogen peroxide is a redox reaction. Always remember one thing about hydrogen peroxide. There are substances that are oxidizing agents, there are substances that are reducing agents. But hydrogen peroxide is one thing which acts as both. Sometimes it can be an oxidizing agent, sometimes it can be reducing agent. That's something special about hydrogen peroxide. And when hydrogen peroxide is involved, you must think about redox reaction. And when there is redox reaction, then the X factor, the valency factor, is calculated by electrons movement. How many electrons are moving? That's how you calculate this valency factors. You don't see how many charge is there on cation, etc. So, how to handle this situation then? Well, you just take it that manganese has got positive 7 character in KMnO4 and it becomes +2 character on the right side after the reaction is done with hydrogen peroxide. Later on you will understand it better when we discuss oxidation reduction reactions. What is the meaning of +7 and +2? So right now we just take it that there is a charge transfer of 5 units per manganese atom. And it is the manganese atom which is the key in KMnO4, not other fellows. So because the charge transfer is of 5, you divide by 5. 158, the molecular mass, that should be divided by 5 for equivalent mass. Right? So 3 grams divided by equivalent weight, and liter is only 1. So that is the normality of KMnO4 solution. What volume of permanganate solution will be required? Let that volume be V. N1V1 equal to N2V2. The hydrogen peroxide solution 20 ml are required. Okay, it is ml, so I should say MEQs are being equated on both sides. MEQs are being equated. This V is in ml. Now this fellow, normality of hydrogen peroxide, 2 grams are there in 1 liter. So 1 liter is here fine. Equivalent weight is required. H2O2 molecular mass will be 2 plus 32, 34. 34. 34 should be divided by what? Now it's a little problem because it is a redox reaction. So I must give you one information which you will certainly understand when we do oxidation reduction topic. In hydrogen peroxide, oxygen has -1 type of character, -1 type. Like I said, manganese here has +7 type of character. Oxygen here has -1 type of character. Generally, oxygen has -2 type of character, but that is something special about peroxides. It has got -1 type of character. And when hydrogen peroxide reacts with KMnO4, then oxygen on the other side has 0 character. So from -1 character to 0 character, in 1 atom of oxygen, you find 1 electron transfer taking place. 1 atom of oxygen, 1 electron transfer takes place. But looking at the definition, it is not per oxygen atom. It is per unit of H2O2. It is per unit of H2O2 that you have to look for electron transfer, not one atom of oxygen, but there are two atoms of oxygen that are there in hydrogen peroxide molecule. One oxygen, one electron. Two oxygen atoms, two electrons. We are talking about hydrogen peroxide, not oxygen. So from 1 unit of hydrogen peroxide, there will be 2 electron transfer taking place. And that is why it is 34 divided by 2, the equivalent weight. Liter is 1. Look at this, gram per liter. So this is the normality of hydrogen peroxide multiplied by the volume which is required, 20 ml. Now you can solve for V and see how much are you getting it, this V. See how much volume are you getting. That should be the answer to this part. Any questions? Yes, go ahead.
Sir, that +7 and -2, is that oxidation state, sir?
That's right. It is +2. +7 and +2 are oxidation states.
Fine, sir. Thank you, sir.
Yes, anything else? Even that -1 is oxidation state, this one.
Yes, sir. Generally, in H2O oxygen state of oxygen is -2 and H2O2 it's -1, sir.
That's right. That's right. Now, I hope you have got this 24.8 approximately ml. That answers this part. Now, coming to this part. You already know what is the molarity of hydrogen peroxide. You know what is the normality of hydrogen peroxide, right? But as I said, in case of hydrogen peroxide, there is another way to tell the concentration. Concentration of something can be told in so many different ways. Now, we want this last answer in terms of what I was telling you, 20 volume type of thing. 20 volume means 1 ml hydrogen peroxide will give 20 ml oxygen by this reaction. Lower, look at that, at normal temperature and pressure. That should not be difficult for us to find out how much oxygen will be liberated. We already know the milli equivalents are these. That comes out to be 20, this 2 will go up, 20 into 4 over 34, this fellow. That's MEQs we already know. If we know MEQs, we know millimoles also. Millimoles will, this 2 will not be there in millimoles discussion. This 2 will not be there. So 20 into 2, 40 by 34, which is 20 by 17. Now, when you write this equation, moles ratio, this is double, this is single. So what millimoles of oxygen are you going to generate? Oxygen gas. Half of this fellow. That means 10 by 17 millimoles of oxygen will you get. You will get 10 by 17 millimoles of oxygen. And that means 10 by 17 whole divided by 1000 moles of oxygen you will get, right? These many moles of oxygen. Now at NTP, 1 mole has how much volume? 22,400 milliliters. So these many moles, 10 by 17 into that, will have how much volume? 22,400 into 10 by this whole thing. Just calculate that. How many ml is that? Oxygen. 3 zeros will cancel. Then 224 by 17. 224 by 17. 13 point something.
13.17.
13.176. Okay. Fine, but
Yes, sir.
but there's one more thing. This 13.176 that much ml is given by 20 ml of hydrogen peroxide. This is given by 20 ml. Look at this line, third line, 20 ml. So 1 ml will give how much? Divide that by 20 and you will get 0.6588, 0.66 ml. 0.66 ml. So it is just 0.66 volume. That's it. We will say it is 0.66 volume hydrogen peroxide strength. That means if you take 1 ml of this hydrogen peroxide solution, then you will get 0.66 ml of oxygen at NTP. Any questions? Let me know. All right, we stop now.